Hello, everyone. So we are going on. We are continuing with the cycle of the lectures, referring to the course survey of optimization offered by the Department of Postgraduate Studies of Viktor Glushkov Institute of Cybernetics of the National Academy of Sciences of Ukraine. I'm reminding you that the course developer is Butenko Sergei, professor of Texas A&M University. The course advisor is Petsyuk Pyotr Ivanovich, Doctor of Sciences, Institute of Cybernetics, and the instructor is I, Valeria Elena Ivan. Last time we did a historical overview of mathematical programming and optimization establishment and development. Today we will come to mathematical programming basics. Now, why do we see the term mathematical programming? In calculus and mathematics, the optimization problem is also referred to as mathematical programming, and we will widely use this term to substitute the word optimization further in the course. Since the invention of digital computers, optimization, or the same mathematical programming, has become one of the most important and well-studied fields in applied mathematics and engineering ever since. So today we will continue with other topics related to mathematical programming. Specifically, the agenda of today's lectures will cover such topics as mathematical programming applications, definition of mathematical programming branches, formulating of optimization problems, some examples of them, terminology and definitions, including decision variables, objective function, feasible region, bonding on bonding constraints, local, global extremums, and so on and so forth, formulating a linear programming model specifically, and some examples of optimization problems. Initially, and still, mathematical programming is a branch of operations research, which comprises a wide class of control problems, the mathematical models of which are referred to as finite dimensional extremum problems. Note that the term mathematical programming is not a term directly related to computer programming. Rather means preparing a schedule of activities, and this term comes from the use of the word program by the United States military to refer to proposed training and logistics schedules, which were the problems being solved actually by George Danzig at that time. Many real-world and theoretical problems may be modeled in the general framework of mathematical programming, and it finds applications in various areas of human activity where it is necessary to choose one of the possible ways of action. For example, in solving numerous problems of control and planning of production processes, as well as in problems of design and long-term scheduling. Encyclopedia of Britannica, Encyclopedia of Britannica, suggests the following definition of mathematical programming. Mathematical programming is a theoretical tool of management and economics in which management operations are described by mathematical equations that can be manipulated for a variety of purposes. If the basic descriptions involved take the form of linear algebraic equations, the technique is described as linear programming. Is more complex forms are required, the term nonlinear programming is applied. So therefore, depending on the types of mathematical equations involved in a model, the following branches are distinguished in mathematical programming. Specifically, linear programming, as it has been mentioned, where the objective function and the constraints are linear. Quadratic programming, where the objective function is quadratic and convex, while the feasible set is defined by linear equalities and inequalities. Convex programming, the objective function and the constraints are convex. Discrete programming, where the solution is sought only at discrete points of x or say integer points of x. And relatively new, actually, relatively like 60 years. Stochastic programming, in contrast to deterministic problem, the data contain an element of indeterminacy. For example, in stochastic problems of minimization of a linear function, the parameters, let's see, sub j, the coefficients, sub j, a sub ij, and actually the p constants, all of them or some of them are random. Formulation of an optimization problem involves taking statements defining general goals and requirements of a given activity and transcribing them into a series of well-defined mathematical statements. More precisely, the formulation of an optimization problem involves 3 steps. Step 1, introduce the decision variables, which are the parameters whose values need to be determined in order to solve the problem. Step 2, state the objective function, which is the quantity is to be optimized as a function of the decision variables. And step 3, specify the constraints, or in other words, the conditions that the design parameters are required to satisfy. Note that the objective function and the constraints must all be functions of all or some optimization variables, decision variables. Let's consider the following example of formulating an optimization problem, very easy one. So the task is create a box with an open top and square base with a surface area of 300 square centimeters. One height will produce a box with the maximum possible volume. So before proceed with the problem, let's analyze the given information. First of all, we're talking about a box, so therefore it really makes sense to sketch such a drawing of a box and look at it more precisely. So we know that a box has a length, a width, and a height. What is important actually for us to know from this problem, that with an open top, so the top, with this top, those wings are not included, so therefore we disregard them. And now the important piece of information is that square base, that the bottom part, the bottom side of the box, the base of the box is a square, meaning that the length and the width are equal. And we don't know anything about the height, it doesn't say anything about the height. So therefore, it makes sense to introduce the decision variables as the height denoted of the box denoted as h, and the side measurement of the box, which is denoted as x. Again, I'm recalling that it is a square base, so therefore the length and the width are equal. Step 2, state the objective function. From the school course of geometry, we remember that the volume of such shape is computed as the length times the width times the height. But as the length and the width are equal and denoted as x, so therefore the general formula will convert it into the volume equals x squared times h, and as the question says, we need to reach the maximum of this function. So therefore the objective function actually has been formulated, has been stated. Step 3 for us is to specify the constraints. Now, which phrases would stand for the constraints in this particular case? So the surface area of the box is a constant of 300 square centimeters. Now, this is an obvious constraint. Let's turn it into an equation of the surface area. Recall that this surface, again, from the same from the same course of school geometry, we remember that the surface area of a square, which is the bottom of this box, is calculated as x squared, just because the length and the width are equal. While the rectangle is on the side, the surface area of one rectangle would be x the side measurement, x times h, the height, but we have 4 of them. So therefore, the second term is represented by the product of 4, x and h. And according to our problem, it needs to be equal to 300. Interestingly, is that the constraint is represented by an equation. And step 1, step 2, step 3 have been performed. So therefore, we can summarize the optimization problem and record it in a standard form. Maximize the objective function of the volume x squared times h. Subject to, the word subject to represents the constraints involved in the optimization problem. The first constraint refers to 300, yeah, so x squared plus 4 times x times h equals 300. And there are 2 more important constraints included into the model, and those constraints refer to the decision variables. As the distances are greater than 0, so they are always positive, so therefore we put the constraints of the decision variables as x greater than 0 and h is strictly greater than 0 too. So therefore, the given optimization problem consists of 3 constraints. One of them is an equality, and the 2 others are inequalities. Note that the objective function is not linear, and the first constraint is not linear either. So therefore, it is not a linear programming problem. Now, as we're talking about mathematical optimization, so let's give a more mathematically formalized definition of optimization problem formulation. Now, let set X be a subset of the Euclidean space of n-dimensional Euclidean space, and be a set of n-dimensional real vector in the form of x of 1, x of 2, x of n, actually, which represent the variables. And f is a given function. Then optimization general form for maximizing is with this one. And the same can be recorded in like more formalized mathematical way as maximum of f of x subject to x's belonging to the feasible area of feasible set x. And actually similar form will refer to the problem of minimization. So minimize f of x subject to x's belonging to the feasible area x, where x of j is called a decision variable, x is called the feasible region, and f is referred to as the objective function. Now, note that the maximization problem, optimization problem, can be easily converted into a minimization problem and vice versa, just by putting a negative sign in front of the function. The set of constraints can be expressed as equalities and inequalities, yeah, and where I and j are indices. There are the description actually covers a wide variety of possible scenarios, and for example, in some problems, the decision variables are required to be, say, binary. Yeah? Recall that binary means actually 2 values can be taken customarily with normally, decision variables can take only 2 values, and customarily we denote them as 0 or 1. So note that the same expression can be substituted by equality x of j, 1 minus x of j equals 0 for binary decision variables. Then inequality constraints can be always converted into a standard form of less than or equal to 0, for example, even if the given initially given condition or constraint is one function is greater than another function. But it is the same as introducing, we can always introduce a function g sub 3 of x, which is no greater than 0, where g sub 3 of x is represented as g sub 2 of x minus g sub 1 of x. So therefore, the initial inequality, this one, can be easily converted into this one. No, and then if the feasible region X is described by a set of equalities and inequalities, equality and inequality constraints, a point X bar is feasible if and only if it is satisfied each of the equality and inequality constraints defining the feasible region X. Since the optimal solution will depend on the constraints in the optimization model, we consider two types of constraints. Specifically, those which change the optimal solution if the constraint is changed, and those which do not change the optimal solution after the constraint being changed. So therefore, with this situation is defined as binding constraint or active constraint, which is the same, or non-binding or inactive constraint at a specific point X. Now recall that actually recall about specific point, which is like a prospective solution. So consider actually the following example where there are two functions represented by two rounds. Yeah. And they intersect in the feasible area X. Here is the intersection X. Now, let's consider 3 points. Well, the first one is X bar. Oh, wait, X hat, sorry, X hat. X hat is inactive and or non-binding for the both functions. Yeah? For the both functions, because it doesn't belong to the boundary and it is located within actually this intersection, within the X variant. Then for X curve, for X curve, we might say that the first constraint is active in point X curve and at point X bar, this point, as it lies on the both boundaries of the given functions. So at point X bar, the both functions are active, are binding. Now, more definitions. Next, we define the concept of a feasible direction, which characterizes a local property of a point in the feasible region, specifically a property that is required to be satisfied only in an arbitrary small neighborhood of the point. Now, a vector D from R of n, from the Euclidean space of an n-dimensional Euclidean space, is called a feasible direction for the feasible set X, which is a subset of Rn, at a point X bar from this actual feasible region, if there exists delta greater than 0 such that X bar, so this is actually the point, plus alpha t belongs to the feasible area region for any alpha no greater than delta. Then X hat, which from the feasible region is an interior point of the feasible region if there exists epsilon greater than 0 such that X hat is included in the feasible region together with the e-ball centered at X bar. And we call the set of all interior points of X, the interior of X, and denoted as int of X. And one more definition about boundary point, X bar from the feasible region is a boundary point of the feasible region if it is not an interior point of X. Any direction is feasible at an interior point. Now, let's consider the following example. Here we have the feasible region X. Okay, it is. No, and here we have several examples here. Now let's consider first the points x prime and x double prime. They are interior points because according to the definition, there is a positive epsilon here, a positive epsilon, which can be drawn around x prime and another epsilon double prime around x double prime, being centered in x prime, and all this area will belong to the feasible region. No, and the same is true about x double prime. So based on the definition, we may conclude that x prime and x double prime are interior points. Now let's consider boundary points. Here it is, here and here, y prime and y double prime. So their boundary, because they do belong to x, but they are not interior, and there is no epsilon which would belong in the whole area. Epsilon ball centered at this point would belong to x. Still y hat and y prime and y double prime belong to x. That is important. Yeah. And about feasible directions, the direction here, d prime and d double prime are feasible directions because they all lie in the feasible region. And directions h prime and h double prime do not lie in the feasible region, so therefore they are infeasible directions. No, and definitely for all interior points, we may say that directions would be really feasible. Yeah, no matter where you draw it, actually, it is feasible. Since we said that the problems formulated as mathematical problems are referred to as finite dimensional extremum problems. So therefore, next we are going to discuss the concept of global and local optima. No, optima stands for either minimal or maximum. Because they are some of the most fundamental concepts in the field of optimization. And this is what we're searching for when we solve the optimization problem. Actually. So what is global minimum? The point x asterisk from the feasible region is the point of global minimum, or sometimes it is referred to as global minimizer, for the problem of minimizing the function subject to axis belonging to x, if f of x asterisk is less than or equal to f of x for all x's from the feasible region. A global minimizer does not always exist, even if the function is bounded from below. So therefore, then we introduce two more concepts, and they are infimum and supremum, which for infimum is represented with its greatest lower bound, and for supremum, supremum is represented by its least upper bound. And here there are the notations of infimum and supremum. Now, to make it actually very easy to comprehend, let's consider an interval AB with the unbounded actual limits. Yeah, so with where limits are not included, then the supremum of this interval will be exactly point B, though point B is not included into this interval, but it is the least upper bound, and A will represent the infimum for the same interval, though A itself is not included into the initial interval AB, so, as we stated. So that is actually about infimum and supremum, which sometimes might substitute minimum and maximum. If f is unbounded from below or above, then infimum value is equal to negative infinity, or supremum will be equal to positive infinity respectively. The point x asterisk from the feasible region is a point of local minimum, or not local minimizer for the problem of minimizing f of x subject to access from the feasible region. If there exists absolute such that f of x is greater than or equal to f of x asterisk for any x from the feasible region within the distance which is less than absolute. No, and here actually what I want to point your attention to with this sign, greater than or equal. If the condition of equality is involved, then we just say local minimum. If the condition of equality is not involved here, then we speak about strict local minimum. In the same manner, we distinguish global minimum and strict global minimum. No, actually, to make it easier, let's consider the following example. This curve, let's consider the feasible region like here, somewhere here, and here, this region, this interval. So points x sub 1 and x sub 2 will represent strict local minimizers because within tiny interval of absolute, any value of fx is taken within this interval would be strictly greater than f of x sub 1. No, and the same is true about f over x sub 2. Then, about this interval, from x sub 3 to x sub 5, all these values will represent local minimizers, a local minima, but they are not strict local minima just because their condition of equality is involved, because you see that literally actually this interval is parallel to the x-axis. So therefore we have in terms of local minima, we have the points x sub 1, x sub 2, and all the points in the interval from x sub 3 to x sub 5. So that is clear. Now about global minima. Out of all these minima depicted in the picture, the global one is represented by x sub 2, and this is a strict global minima because no other minima is lower than the function value at the point x sub 2. And as we are slowly proceeding to and moving forward towards linear programming optimization problems, so therefore it really makes sense to remind you a definition of a linear function. Well, first of all, a linear function has a form of a polynomial c sub 1 times x sub 1 plus c sub 2 times x sub 2 and so on and so forth, c sub m times x sub m, where c sub 1, c sub 2, or denoted as c sub jeta, where j may vary from 1 to n are constants or coefficients at x, and x sub g represent the variables. So therefore the functions of this type is a function of this type is called a linear function. Now, if there is only one variable involved, only this, for example, so the linear function has can be graphically represented by a line on a plane. Here it is an example of that. If we have two variables involved with the linear function, then it can be graphed as the plane in a three-dimensional space. So this is the linear function, and this is a non-linear function. So this is just to remind you the definitions of being linear. No, and the last issue which we planned for today is formulating a linear programming model example. Let's consider the following application. Heavenly Pouch Incorporated produces two types of baby carriers, non-reversible and reversible. Each non-reversible carrier sells for $23, requires 2 meters of a solid color fabric, and costs $8 to manufacture. Each reversible carrier sells for $35, requires 2 meters of a printed fabric, as well as 2 meters of a solid color fabric, and costs $10 to manufacture. The company has 900 meters of solid color fabrics and 600 meters of printed fabrics available for its new carrier collection. It can spend up to $4,000 on manufacturing the carriers. The demand is such that all reversible carriers made are projected to sell, whereas at most 350 non-reversible carriers can be sold. Heavenly Pouch is interested in formulating a mathematical model that could be used to maximize its profits resulting from manufacturing and selling the new carrier collection. Now, the first step we need to do before processing the information, probably we need to read the problem carefully again and to analyze the given information. Likewise, we did for the previous optimization problem where we really made a drawing of the box, and it really helped us to determine the decision variables and actually the constraints, how to formulate it in mathematical symbolism. Likewise, here we would recommend actually to systemize the data somehow. Now, first of all, we can distinguish that there are two products produced, and we call them non-reversible carrier and reversible carrier, and there is a lot of information given for each item produced, manufactured. So, which information and which sources and hidden sources actually are included, are given in the problem about those goods. Now we know the selling price for the both products. For non-reversible carrier, it is $33 selling price, and for reversible, it is $35. Then we know that the input is fabric used for the both items. Moreover, we distinguish two types of fabric: solid fabric and printed fabric. As for the solid fabric, it is used for the both items, for the both goods, and the same volume is required for them, 2 meters. And printed fabric is used only for reversible carriers, and again, we need the same 2 meters of this fabric. Then the manufacture costs are known for the both goods. For non-reversible carrier, the manufacture cost is $8, and for reversible carrier, it is $10. Now, that is in short about what we have, but we actually have some limits spelled out of the problem. Now, let's find them. Limits. The company has 900 meters of solid color fabrics and 600 meters of printed fabric available for its new carrier collection. So therefore, the limits will go into the last column of the table and represent the solid fabric actual limit and printed fabric limit. Then we have a budgeting actual limitation that the company can spend up to $4,000 on manufacturing the carrier. So therefore, there is no budget limitation normally included in such kind of problems. In the marketing constraint, saying that at most, meaning that no more than 350 non-reversible carriers can be sold. So we will put these limitations right here. So after having such a table with really systemize and analyze the given information, it's quite easy to identify and their reasonable actually decision variables, and definitely they will go for the number of units produced of non-reversible carriers, and we will denote them as X of 1, and the number of units produced for reversible carriers, and we will denote them as X of 2, which is clearly reflected on this slide. So X of 1, the number of non-reversible carriers to manufacture, and X sub 2, the number of reversible carriers to manufacture. Step 1 has been performed. Now about the objective. The problem states that the objective of Heavenly Pouch Incorporated is to maximize its profit, which is the difference of the revenue and manufacturing cost. The revenue is calculated as selling price times the number of units produced, In our case, we have two products, so therefore the total revenue is represented by the formula 23 times x of 1 plus 35 times x of 2. Recall that 23 represents 23 and 35 represents selling prices for the given product. And the cost is calculated as the cost of the unit, manufacturing cost of the unit produced, times the number of units produced. As we have two different items production, so therefore for non-reversible, the production cost was stated of a unit was stated as $8. For reversible carriers, the production or the manufacturing costs per unit were stated as $10. So therefore the total cost is calculated as 8 times x of 1 plus 10 times x of 2. Now for calculating the profit, we know that the profit is revenues minus manufacturing costs. We literally plug in the given values instead of these variables, and after distributing the parentheses and performing algebraic simplifications, we come up with the expression 15 times x of 1 plus 25 times x of 2. And slowly we are moving towards this constraint specification, the condition that the design parameters are required to satisfy. Now, the first limitation of constraint was given about meters of solid color fabrics available. So that was 900 meters. As we need 2 meters to produce 1 unit of reversible carriers and 2 meters to produce 1 unit of non-reversible carriers. So the total amount of the fabric required to produce the both goods will be 2 times the number of units of one item plus 2 times the number of units of the other item. And it's set to be less than or equal to 900 or no more than 900 meters. After performing their simplification, we come up with the inequality x of 1 plus x of 2 is no greater than 450. No, I'm just reminding that division by a positive number doesn't change the direction of the inequality. Now, in the same manner, we actually developed the constraint for printed fabrics and come up with the inequality x of 2 less than or equal 300. So only x of 2 is involved because printed fabrics is not used for non-reversible carriers. So therefore, only one variable is involved into this inequality. The other constraints will refer to budgeting. Heavenly Pouch spends $8 per unit and $10 per unit to manufacture non-reversible and reversible carrier respectively, and they cannot spend more than $4,000 on manufacturing. So therefore, the total manufacturing cost will be 8 times the number of units of non-reversible carriers plus 10 times the number of units of reversible carriers. So no, and it says to be less than or equal to 4,000 or no more than $4,000. After again performing standard simplification techniques, we come up with the inequality of 4 times x of 1 plus 5 times x of 2 is no more than $2,000. Remember that we are talking about dollars. And actually the last but not the least constraint refers to demand constraint, demand limits. It said that no more than 350 non-reversible carriers can be sold. So therefore, it in mathematical symbols, it can be converted into an equality of x of 1 less than or equal to 350. The summary, the complete linear programming formulating will look like this. So the first line, maximize, will represent the objective function, which refers to profit maximization. Subject to, the words needs to be spelled out, of course, will refer to a set of inequalities given in the problem, yeah, suggested in the problem. So the first constraint refers to the solid color fabric volume, then to the printed fabric constraint. Next, the third inequality refers to the budget constraint. The 1, 2, 3, fourth inequality refers to the demand constraint, and we added 2 more constraints on the decision variables, stating that they cannot be negative. So this is a non-negativity constraint for the decision variables. So therefore, this is the standard form of presenting optimization model in linear programming. Now, in the assignment, which I posted on the site in the Google Classroom, you are to solve one of the problems at the end of the chapter. The number of the problems are stated there. You may choose one of them, you may solve all of them. Actually, it all depends, but at least one. Please, while presenting your findings, please follow their logics and their hints presented actually on the slides. So therefore, what you will need to do is clearly systemize the information, if it is possible. It might be a table, it might be a drawing, if it is appropriate. So therefore, give me some sort of analysis of the given information. And then please clearly explain what you do at every step. So clearly put step 1, introduce the decision variables. Step 2, state the objective function. Step 3, specify the constraints, and actually analyze the given information, how you come up with the objective function. And in the same manner, please, but like I did, I really extract some words which would relate to every constraint and put it in wording here. So therefore, explain how you come up with the final model, optimization model to be solved actually later on. Remember, hints for formulating LP optimization models. Remember that if we are using indices, clearly specify the meaning of indices and their range of values. For objective function, when writing the objective function, remember to indicate whether you are minimizing or maximizing it. And for the constraints, make sure that along with the given limits and constraints, you specify whether each variable is non-negative or real, or might be some other limitations on the decision variables, but decision variables need to be included into the final optimization model. So with this, thank you very much. I appreciate your comment here. The video will be posted on the site. Wait a minute, I will